system level analysis. Also, the data was problem specific. If it's flow through a tube, use this data. If it is flow over a cylinder, use this data. So, we would like to go beyond a device level characterization of the flow to device independent analysis. We want to have an analytical approach that will hold for all devices. Once you have that kind of a formulation available, then you can probably predict how each device is going to behave. Then you can say, okay, this is flow through a tube. You have analysis where you start with just the flow field, and then the geometry appears as boundary conditions. Flow phenomena along with boundary conditions will take you from a local description of the flow field to a device level description. Then you can explain why friction factor in Moody's diagram has that particular shape. So, we also talked about local versus global earlier. We said you can go from local to global by integrating the flow field. If you integrate velocity, what will you get? Flow rate. If you integrate stresses, what will you get? Forces. And if I give you the total force, you cannot obtain the stress distribution. If I give you the flow rate, you cannot get the velocity distribution. You can get only the average velocity. So, that makes local more general than global. So, that will be the major change in the direction of this subject post your mid-semester break, or I should say post your mid-semester exam. So, hopefully, you can get your answer sheets tomorrow in the tutorial. I think class average is probably 14 out of 30, and highest probably is 27 out of 30. Also remember, you have a second tutorial on Saturday. This Saturday is going to be like a Thursday, because the following Thursday or some Thursday is a holiday. So, they have scheduled this Saturday as Thursday. So, you have at 11 o'clock you have a tutorial again, and the questions will all deal with local analysis, which means velocity. Now, you no longer talk of velocity is 3 meters per second. That is not the approach. Now, you are talking about velocity distribution in space and time. Speaking of your mid-semester exam, there were a few cases of, I am sorry to say, malpractice. So, those students will be spoken to directly. So, I hope it does not happen in the final exam. So, in this local analysis, the flow rate is discussed in terms of the velocity vector. Now, we have discussed all real life problems are three-dimensional, but 3D analysis is algebraically daunting. So, most of the time we look at 2 dimensions, assuming nothing very significant happens in the third dimension. And more often, I should say quite often it is 2D, more often or most often it is 1D. That means it's only one velocity component. But there could be a dependence on multiple dimensions, symbolically shown as x and t. X vector, this tilde represents vector. Similarly, the forces are expressed in terms of stress. You remember that stress is force per unit area, but force is a vector, area is a vector. That makes sigma dependent on 2 directions. One is the direction of the force, the other is the direction of the area vector. So, it is now while developing this part of the subject, I will not say anything new, but I will keep referring to all the discussions we had at the start of the course. You may remember that we talked about finding u and sigma and then integrating them to find flow rates and forces. Okay. You will remember Newton's parallel plate experiment. You will remember the discussion on a Newtonian fluid. Newtonian fluid is one for which viscosity does not depend on, we said, strain rate, which is just the velocity appearing in the flow field. Okay, constant. So, when you prescribe viscosity mu equal to something, you are really insisting on the medium being Newtonian. So, please keep referring to the initial discussions of this course. Okay. Now, what are the physical laws? The physical laws continue to be mass, momentum, energy, and second law of thermodynamics. But you will also recall that to solve that system of equations, we brought in handbook data. Okay. So, that handbook data was device specific. So, when you go away from a device and you talk about just the flow field, for example, this air flowing here, you do not refer to the context of air flowing in a room. It could be flowing here or flowing outside, or it could be just air coming out of my mouth, or air coming out of the exhaust of an engine, or it could be flow of air past an object that is moving. It is just the flow, you are not referring to the context. Then there is no handbook data. Instead, you have to rely on material data, material here being the fluid medium. So, instead of handbook data, we will now bring in material behavior. What is material behavior? So, that we will discuss as we go. So, these are some small aspects which differentiate our global approach vis-a-vis the local approach. But local is more general, that is what I have been saying, that if anything more general will also be more complicated. So, on the face of it, it looks complicated. Let me not mince words, it is complicated. Okay. So, how complicated, that we will see. In the meantime, for the lecture of today and the lecture of Friday, I will rely on some results that are available to you in vector calculus. Do not ask me how did you go from this integral to that integral. So, we do not have an opportunity to derive identities. Those are available to you in books on vector calculus. So, these books are also called books on engineering mathematics. The favorite that it's my favorite, let us say, is an engineering mathematics by a book by an author whose name is Erwin Kreyszig, and I was told many of you are familiar with that book. Kreyszig, does it ring a bell? It rings a bell. So, you know this name, Kreyszig? Kreyszig. Now, generations of engineering students have referred to that book. So, like this book by Frank White, this book on engineering mathematics is used by second year and third year undergraduate students all over the world. So, I am not saying anything extraordinary. And these results of vector calculus are given in those books, in that book. So, I do not have to derive those results, I will just use them so that we can go through the formulation and then arrive at a conclusion out of it. Now, we have done some amount of local analysis already. We started with mass balance. And we were able to derive a local form of the mass conservation equation in this form, where del dot rho u is interpreted as mass inflow minus mass outflow. If the two of them do not match, it will lead to change in density of the material. This is happening, of course, at the scale of the control volume. It is also happening at the small scale. Rho, what is rho? It is density at a point, at a given instant of time. Okay. So, the principles of conservation of mass and momentum, energy, they are all now being applied to a point. So, just imagine the versatility of these laws. Laws, LAWS, not your friction loss or head loss. So, that is LOSS. So, sorry about the mix up of terms. And then we also had rho equal to constant, del dot u equal to 0, and if del dot u equal to 0, then a stream function will exist. Defined as where u and v are the x and y components of velocity. The advantage of using a stream function is it can help you visualize the flow field. If flow goes around the object, then the velocity vector is tangential to a constant stream function line. A constant stream function line is called a stream line. So, stream line is a curve on which stream function is a constant, and stream function is a function of x and y from which you can derive the velocity components in this manner. and this velocity field will satisfy del dot u equal to 0. Therefore, it is a representative of an incompressible flow field. So, the same thing being said in many different ways. So, on a streamline, psi is constant. So, if this is psi equal to constant, then the velocity vector is tangential to it everywhere. So, the flow normal to a streamline is 0. So, if you have a solid object and there is no flow normal to that, it could be a flat plate. So, a flat plate is a streamline. Okay. If you have a circular cylinder, there is no flow normal to the surface of the cylinder. So, the surface of the cylinder is also a streamline on which psi is constant. Now, in many of the calculations in the first part of the course, we treated the flow to be incompressible. We will continue thinking of it that way for some more time. So, the applicable form of the mass balance equation will be del dot u equal to 0. So, in Cartesian coordinates, will become u x, which is partial derivative of u with x, partial derivative of v with y, sum of the two is 0, which is del dot u equal to 0. U and v are the x and y components of velocity. Del dot u equal to 0 is in coordinate free form. So, if you want the expression in any other coordinate system, you have to define your del operator and the velocity vector in that coordinate system. So, if you go to a polar coordinate, polar is r theta, cylindrical would be r theta z, then you also have spherical. Okay. So, spherical is more complicated algebraically. Also harder to visualize. So, in view of the time constraint of this course, I will not refer to spherical and I will not make you work on spherical coordinates. So, that will help you focus. Please look into problems related to Cartesian coordinates, polar coordinates, cylindrical coordinates. Spherical we can set aside as far as class work is concerned. This notation suffix u suffix x indicates partial derivative. Partial derivative. Why partial? Because u can be a function of x and y. So, when you differentiate, it is partial derivative. It can be a function of time also. So, this del dot u equal to 0 does not have time. So, does it mean steady state? No. It holds for both steady and unsteady, because the only time dependent term in mass balance is this del rho del t, and if rho is constant, that term is 0. So, this del dot u equal to 0 is both for steady and unsteady. All right. So, this is mass balance. Then we go to the momentum equation. So, just recall that this is your control volume, this is control surface, and there is a flow field that is being analyzed, and then we had the momentum equation written as sum of all external forces equal to essentially mass times acceleration evaluated over the control volume. So, this is a global version of the momentum equation. So, it should be there in your notes. I am not writing anything new. So, the rho dV is mass, elemental mass, integrated over the control volume is total mass. So, the bracketed term is acceleration. The first term is often referred as temporal acceleration. The second term has spatial derivatives, so it is called spatial acceleration. The sum of the two is total acceleration of a material element. So, you also remember that this whole thing is the total change. Now, you have to recall total derivative versus partial derivative. So, total derivative of u with time, okay, as the fluid particle moves from one point to another along its flow path, okay, that is du dt, d being this letter d, while the expression in terms of partial, the two are equivalent. What is this form called? Du dt is called the Lagrangian form of acceleration. So, I hope you recall these terms from our previous discussion. So, in global analysis, how did we deal with acceleration? We converted volume integral into a surface integral, and you had some u dot n ds and all that. And then we evaluated the integral by approximating velocity distribution as just an average velocity. So, that is how we were able to evaluate this side, but now you want u as a function of x and time. So, now we have to live with these expanded forms without approximation. And so, these two are equal. This is the material derivative. So, this is the flow path. So, this is the fluid is moving along this line, and if you evaluate the derivative, in the limit, this will give you du dt. What is the other form, the longer form of acceleration? What is it? The two are equal. What is that form called? The longer form, Eulerian, right? The longer form is called Eulerian. Now, this Eulerian form looks more complicated, but it is preferred to the Lagrangian form. The reason is the Lagrangian form has to be evaluated along the flow path, but you do not know the flow path to start with. So, that derivative du dt, the Lagrangian form, cannot be evaluated, but the other derivatives, let us say del u del t, it is at a point. At a point, you just find the change in velocity with time. So, those are similarly del u, that will involve the derivative of u with x partial derivative and partial with y. Those are all in x direction for given y given time. So, those derivatives can be evaluated, they do not depend on the prevailing flow field. So, the Eulerian form is what is preferred in calculations. So, the acceleration vector will have components x and y So, if you want to evaluate this quantity, it will just be u v dot product u x u y, which is u x plus v u y. Okay. So, this term will be u v x plus v v y. What is u x? Partial derivative. Do not forget that a term such as v x will be this partial derivative. Okay. So, these are the acceleration components. So, if the flow field is steady, that is, it is not changing with time, then the time derivatives are 0. That does not mean the fluid is not accelerating. It can still accelerate because of the spatial terms. Okay. So, a familiar example, in fact, in the tutorial you are given a problem where you have, let us say, a nozzle, and because of the reduction in cross sectional area, the velocity is progressively increasing in the flow direction. So, the derivative of u with x is greater than 0. So, that is an example of spatial. So, u x in this problem, in the nozzle problem, will not be 0, it is greater than 0. Okay. Similarly, in a diffuser, velocity is decreasing in the flow direction. So, u x will be negative. Okay. So, the spatial terms, so this is spatial acceleration, even though the temporal terms may or may not be 0. Okay. Suppose you have an engine operating. So, in the combustion chamber of the engine, velocities are changing with time, actively changing with time. So, there are examples where flow can change with time, there are examples where flow does not change with time. Similarly, flow field can have a spatial acceleration component or may not have a spatial acceleration. So, the time, that is temporal and spatial acceleration terms, are independently prescribed. Okay. So, temporal acceleration, spatial acceleration. The sum of the two will give you the Eulerian form of fluid acceleration. Okay. So, now this equation f equal to integral C v rho acceleration d v, this form, this is a global representation of the momentum equation, and now we have to go from global to local, and that we do by shrinking C v to a point, that is one approach, or have an equation where C v becomes redundant. If it holds for any CV, it holds for every CV. So, that means it holds pointwise as well. For that, the force field has to be expressed in the form of an integral. So, this force field in the most general setting can be split into body forces and surface forces. Body forces will act throughout the volume of the fluid contained in CV, and surface forces will act on CS, the boundary of CV. So, these body forces most of the time the body force field is independently prescribed. One example of the body force field you have seen is gravity, okay, which is independent of the flow field. Whether fluid moves or not, gravity field is intact. We also said in our discussion there is no change in acceleration due to gravity over the scales of interest. So, it is written as body force field per unit volume integrated over CV. So, suppose the body force, it may arise from an electric field, magnetic field. For our discussion, it is a gravity field. So, this okay, I think I forgot to send you that list of Greek symbols. Did I send you that list of Greek symbols? Safe to say no. Okay. That puts the burden on me then. I think this symbol, it is a Greek symbol, it is either kappa or chi, I am not sure. Chi? Chi? Okay. Chi. Okay. So, that is let us say chi, then if it is a gravity field, then mg is the gravitational force per unit volume will be rho g, but it is in the downward direction, and if k unit vector k is in the upward direction, you write it as minus rho g k. Okay. And it is independent of the flow field if rho is constant. So, the body force field also can get coupled to the flow field if the fluid were to be compressible, then rho will change from point to point. But for the incompressible field, rho is constant. And the surface forces get connected to the stress tensor. The stresses are forces per unit area, but what area? Surface area. Therefore, sigma is connected to the surface forces. So, let us say you look at a portion of the control surface, I am just exaggerating, a part of the control surface, and that portion is given a symbol ds. It is a part of the control surface. So, it will also have its own unit outward drawn normal. So, to understand sigma, the stresses acting on this element, we may decompose the element into its Cartesian components. Why Cartesian? Because our sigma, we have looked at sigma prescribed in terms of its Cartesian. It is a Cartesian representation of sigma. So, recall that surface forces are defined in Cartesian notation in this manner. It is a 2 by 2 matrix. If you think of a vector, it will be a 1 by 2 matrix, just one row with 2 columns. So, vectors will be 1 by 2, second order tensors will be 2 by 2. So, in 3D it will be 3 by 3. So, that helps you carry out all these dot products. So, the graphical representation of sigma So, this is a small fluid element on which we show all the stresses acting on the individual phases. It is a Cartesian representation of sigma. So, because sigma is available to us in Cartesian form, we also decompose the element ds in Cartesian coordinates. If you had it in polar form, then sigma will be in polar form, ds also will be decomposed into polar coordinates. Okay, so, let us think of this element. So, this vertical stretch would be dy and the horizontal stretch is dx. So, sigma xx, sigma xy, sigma yy, sigma yx. So, using the notation, those are the stresses acting on the element ds, but now we have shown it in let us say component form. So, on the small element ds, the total force acting on it in the x direction is sigma xx dy minus sigma yx dx, and dsy is sigma xy dy minus sigma yy dx. Sigma xx multiplied by the vertical dimension, because force is stress into area. dsx, dsy, these are the components of an elemental force acting on the surface ds of the control surface ds. So, what is the advantage of this calculation? Then you can integrate and get the total surface force acting on it. Okay. So, F we have the first term is the body force component, and then you also will have, you just add to it the surface force in terms of stresses. Okay. Now, recall that see there is a unit outward drawn normal So, there will be a unit outward drawn normal here, and NDS will have components. There is an x component which is dy comma minus dx. The x and y components of the outward drawn normal are dy and minus dx, okay. Which means dsx dsy can be written as n dot sigma ds. Okay, it's you can just do a dot product of n and sigma. This sigma is given to you, n is given to you. You do a dot product of n and sigma. So, 1 by 2, 2 by 2 matrices, you multiply them together and you will get that expression dsx dsy, simple multiplication. So, f is equal to integral Cs, I think dV. Now, here comes the vector identity. Where del dot n dot sigma is replaced by del dot sigma. N dot sigma on control surface is del dot sigma over control volume, and this is equal to integral C v rho times acceleration see, we are not saying anything new. Left hand side is surface forces plus body forces, sum of all external forces equal to mass times acceleration. So, the same story continues in a different form. This form is useful in coming up with a local description of the flow field. Why local? This is still C v. Now, the choice of C v is still unspecified. You may shrink it to a point or just drop it. Since it is not specified, it follows that normally we write this acceleration term on the left. So, this is the local form of the momentum equation. And to be supplemented with the mass balance equation. Okay, so this is a local description of the flow field, which is representative of the physical laws of mass and momentum. Momentum is Newton's second law of motion. Okay, so you will appreciate it is device independent, whether it is flow through a tube or flow in a pump or flow in a reservoir, flow in a nozzle, flow in a room, etc. The same equation will hold. You will also appreciate that the equations are in coordinate free form. You can't solve these equations straight away because those techniques given to you in books of Kreyszig, for example, they require you to convert these equations into a specific coordinate system. You first have to bring in del as a Cartesian operator or a polar coordinates operator. And then you have a certain structure and then you use certain techniques. Techniques are coordinate system dependent. So, but the formulation is independent of the coordinate system. So, in this equation u is the velocity vector which appears in both equations. You have acceleration in the first, in the momentum equation, and it appears as a vector field in the mass balance equation. Chi is a body force field which is specified. If it is gravity, it is just minus rho g k. So, that leaves us with sigma. So, we know the components of sigma, but sigma has in 3D it is a 3 by 3 matrix, 2D it is a 2 by 2 matrix, let us say 2D. So, there are 4 components of sigma, and these change from point to point. So, they are all distributed over the flow field. So, sigma here appears as a quantity that requires to be specified. So, before we specify sigma, let us see what we know about it. So, we always keep referring to a stationary fluid. Suppose the fluid medium is stationary, what do you know about velocity? 0. Velocity is 0. So, the mass balance equation is identically satisfied, acceleration is 0. So, you get chi plus del dot sigma equal to 0. What is that equation called? Long ago we did fluid statics. It is the equation of hydrostatics. So, if the flow is stationary, is sigma 0? No, del dot sigma is balanced by the weight. So, how much is sigma in a stationary medium? So, we are talking about properties of sigma in a stationary medium. Stationary fluid medium, u equal to 0, and these are our components. What are the shear stresses in a stationary medium? Shear stresses in a stationary fluid medium are 0, because the fluid cannot sustain shear stresses howsoever small. So, if it is stationary, I can hear the bells, sigma x y and sigma y x are 0. So, this is symbolically written as sigma I j equal to 0 when I is not equal to j, and when I is equal to j, what is sigma? Pressure in the medium, the normal stresses with a negative sign. The normal stresses will appear as pressure in the fluid medium. Okay. So, sigma I will be equal to minus P. So, we will continue with this discussion on Friday on stresses.